Okay, we're going to pick up here with chapter 16 as we finished chapter 15 last time. A reminder again, the exam will obviously cover what we just quizzed on there, 13, 14, and 15, which is 1 week from today. We're going to take it during lab time. And then obviously 16 will not be on there and stuff. So we're into chapter 16, which is the second to last chapter we're going to talk about. So we're almost there. We're going to talk about acids and bases in this chapter. So let's get into it about acids and bases here. So first off, acids were first recognized by their sort of sour taste, things like vinegar, which is acetic acid, like we did that titration, I think last week using that, things like citric acid. Typically acids will turn what's referred to as litmus paper red. So usually if you're using, for example, blue litmus paper and turns red, really in general, if the litmus paper turns red, stays red, it's usually an acidic type of solution. In addition, acids will do a lot of single replacement reactions. So we saw some of these earlier on in the semester. For example, if you took some zinc and some hydrochloric acid, the zinc would come in and kick out the hydrogen, creating zinc chloride and some hydrogen gas. So I know there was like a ton of experiments where we did that. You created bubbles, you held your finger up and sort of did your wood splint and those type of things. Bases, on the other hand, are characterized by bitter taste. They are slippery. A lot of soaps, drain cleaning solutions, they are like bases. Used to be able to go, so you used to be able to go like Home Depot and buy like almost straight sodium hydroxide to clean your drain. Came in a plastic bottle with gloves and a lot of warnings and stuff like that. But a lot of those guys are basic. Bases are sometimes referred to as being alkalous, or alkaline is another word that's very commonly used to mean base. And if you think about it, as we'll talk about, and we might have talked about before, a lot of strong bases come from group 1 and 2 on the periodic table. And if you remember the names, obviously, of those guys, that is your alkali metals and your alkaline earth metals. And again, really both of those names mean basic. Bases will also turn litmus paper blue. So typically, if you're sort of testing a solution using litmus paper, and like I said, there's kind of 3 types usually. There's red litmus paper, blue litmus paper, and neutral litmus paper. Again, if your paper turns red or stays red, acidic. If your paper kind of turns blue or stays blue, basic is basically what those refer to. Any questions on that there? Now, sort of a very early definition of an acid and base came from a guy named Arrhenius. He did a lot of work with electrolytes. If you remember, electrolytes are those guys we talked about that break apart into ions in solution. And really, because of the presence of those ions, they're able to really kind of conduct electricity, as we talked about. The light bulb coming on or not coming on type of thing. And he defined basically an acid as a substance that's able to produce hydrogen ions in solution. So when we talk about hydrogen ions, that is our H+ in solutions. While he basically characterized a base as something that's able to produce hydroxide ions in solution. So really, it is the presence of free H+ in solution or free OH- in solution, and really the ratio of those 2 things in a solution as to whether or not that solution will be acidic, basic, or neutral if they happen to be equal to each other. One really important thing as we go through acid and bases, you will see really 2 sort of symbols to represent acids. H plus and H3O plus are essentially equal to each other. That is obviously the hydrogen ion. That is what is known as the hydronium ion. And there's a reason you get one versus the other. It just has to do with whether or not, for example, in the equation, you sort of include water. If you do include water, you'll get H3O plus. If you don't, you'll get H plus. So what I mean by that is if you took something like hydrochloric acid, which is really a strong acid, in solution or water, it will break apart into H plus and Cl minus. And this is one way that you could represent that happening of HCl or hydrochloric acid in water. Another way you could represent it is actually include the water in the equation. And basically what will happen is this guy will send over an H plus and we will get H3O plus and Cl minus. So these are two really equivalent sort of equations, if you will. They both represent basically the strong acid breaking apart in solution, which is basically just water. And again, in this case, a lot of times I will write it like this, and a lot of people will, but you'll see books and stuff kind of use the H3O plus because it'll include water a lot in the equations. So anywhere in this chapter where we are writing an equation or we see a formula, if I write H plus, you could pretty much substitute H3O plus in its place. They are pretty much interchangeable in acid-base chemistry. They basically represent the acid part of a solution. And again, it's important to understand that what we are referring to here, like I said, is really free floating amounts of H plus or OH minus in a solution, not attached to anything, just by itself kind of floating around is really, what again makes a solution either acidic or basic depending on the ratio. If you have more H plus in the solution, it's going to be an acidic solution. If you have more OH minus floating around in the solution, it will be a basic solution. And as we'll talk about, they're really tied to each other. As one goes up, the other goes down. So as you see an increase in H plus, you see a decrease in OH minus and vice versa. Any questions on that there? Obviously, that is not an equal sign or anything. So this was a pretty good sort of starting definition of acid and bases. It was a little bit limited in terms of, since he dealt with a lot of electrolytes, a lot of strong electrolytes, he dealt with a lot of bases that actually had OH minus in it. And and so we needed sort of a more general definition of an acid and base. And here's just, again, an example of basically how you get something like hydrochloric acid. You take some hydrogen chloride gas and you bubble it in some water and you get some free H plus and Cl minus, which again, the presence of that guy, acid, presence of this guy, a base. And same thing here, obviously you take some sodium hydroxide solid there and dissolve it in water to do it. That also, when you are sort of looking at an equation, those are really big flags that you're probably dealing with an acidic type situation. If you look on the product side and you see H plus or H3O plus on the product side by itself, same thing here. If you see an equation, you see OH minus on the product side, that is usually some type of basic sort of situation that's occurring. So if you see an equation, especially with acid and bases, if you see either one of those things produced on the product side, you can make a fairly safe assumption that it is going to be an acidic type situation if there's H plus or H3O plus, or a basic situation if you have OH minus. So as I mentioned before, his sort of definition was a really good sort of step forward. But again, he did focus a lot on hydroxide as being part of the bases. And not all bases have hydroxide in it. A lot of strong bases do. So things from group 1 and group 2 on the periodic table that has hydroxide, like sodium hydroxide or potassium hydroxide, calcium hydroxide, and so forth. These guys are strong bases. They actually just kind of carry the hydroxide with them, which is why they are strong bases. But not all bases are strong. There are weak bases. as we'll see a little bit in this chapter. For example, something like NH3, which is ammonia, is a weak base. When it reacts with water, it will actually accept an H plus, and the result of that is you will get NH4 plus and OH minus. So once again, if you look on the product side here, we see OH minus, and again, it is going to be a base. The NH3 doesn't carry the OH with it, but does need to do a reaction with water to produce it. But because it's able to produce OH minus in solution, it's considered a base. It's considered, as we'll talk about, a much weaker base than sodium hydroxide, which once again pretty much just needs to go for a swim, and it's going to break apart into these two things and produce hydroxide right away and really quickly. And again, that's why it is a strong base. We also see something we talked about when we talked about with electrolytes, one-way arrow, 100% breaks apart. Something like ammonia, you have the two-way arrow there, which means it's more of a weak electrolyte, which again is why it is also a weak base. Any questions on that there? So a more general definition, and usually oftentimes what most people think about when we talk about acid and bases is the Bronsted Lowry definition of an acid and base. And the Bronsted Lowry definition is an acid is a proton donor, while a base is a proton acceptor, and a proton is another word to refer to H plus. And that is because hydrogen has one proton and one electron and no neutrons. So in order to become positively charged, it has to lose an electron, which leaves it just a proton. So that is why it's referred to as just a proton sometimes. So this guy also referred to as a proton. So acid will accept the H plus, a base will accept the H plus, and an acid will donate the H plus over to it. So for example, in the little equation I just wrote a second ago, our NH3 plus our water. In this case, it is the water donating an H plus over to the NH3, which means in this case, water is acting as an acid, and NH3 here is going to accept the H plus, which means it is acting as a base. The result of that is what I wrote on the previous slide there. We get this guy and some OH minus that is formed. We can also see that even if you look at sort of the acid breaking apart there in water. In this case, the acid is going to donate its H plus over, and the result of that will make H3O plus and Cl minus, where again, this obviously would be the acid, and in this case, water would act as a base. You can see in this example here, there are things that are able to act as an acid and a base, depending on the situation, and those things are what are known as being amphoteric. An amphoteric substance is a substance that can act as an acid or a base. And water is a prime example of that. In certain situations, water can act as an acid, and in other situations, it can act as a base. So there's several things that can kind of do both things, depending on sort of the situation. Any questions on that there? Now, the consequence of sort of this accepting and donating of the H plus, and by the way, what we're talking about here is really just one H plus. That is the only thing that is being donated or accepted. And the other part of that is it is not just a hydrogen, but it is a plus. So it does affect the charges of everybody on the other side of the equation when that happens. So the result of that is it creates what are known as pairs on each side of the equation. And HA is just a generic formula used for an acid. That's just a generic acid. Remember that when we talk about acids, as we did when we talked about naming, and every acid, the cation is always H plus. So that is always your cation or your positive guy. And then obviously the anion would be your negative guy that is there. And that's basically H with whatever it may be. It could be HCl, which would be hydrochloric acid. It could be HNO3, which would be nitric acid. And I'm sure we remember the naming of those as we talked about, right? How to properly name those, whether or not it contains oxygen is the key thing there, right? If it does not contain oxygen, it is hydro something like HCl, hydrochloric acid. If it does contain oxygen, it is going to have a polyatomic ion like NO3, which is nitrate, which is why that is nitric acid, right? And if the polyatomic ion ends in ITE, it is OUS acid. So like HNO2, right, would be nitrous acid because that is nitrite, right? A free reminder of nomenclature in this chapter here. So when we look at this, the acid on one side, again here, he's going to donate his H plus over to water, which is acting as the base. The result of that, when it donates over its H plus, it creates on the other side what is known as the conjugate base. So the acid on the left-hand side is partner on the other side is what is known as the conjugate base. And same thing happens with our base. The base will accept that H plus. The result of it accepting the H plus is it will form the conjugate acid on the other side. So these two things are related to each other, and they are related to each other by just this guy right here, one H plus difference. So the acid in its conjugate base has one less H plus. And the base conjugate acid has one more H plus, and it is the same H plus that is basically transferred in this process. So that's a really important thing to understand, that an acid and conjugate base or base and conjugate acid, the absolute only difference between those two should only be an H plus. If you have anything that is related to each other, but is more than an H plus, two H pluses, three H pluses, an H plus, an O, something like that, they are not going to be pairs. So the absolute only difference between them has to be one H plus in this particular case. Any questions on that? Also, pretty much left-hand side of the equation is where you find your regular acid and bases. Right-hand side of the equation is where you find the conjugate acid and conjugate base partners on the other side. So on the product side is always where you find the conjugate guys. The regular acid and base always found on the reactant side. So again, if we look at HCl here, we could find our pairs. We see here with our HCl and water, once again here, this is going to be our acid. Water is going to be our base. So we see the HCl donating that H plus over. The result of that is its partner on the other side is Cl minus. And again, if you just add H plus back to Cl minus, you get HCl. Or you subtract H plus from HCl, you get Cl minus. And once again here, our water acting as our base, accepting that H plus, which means on the right-hand side, it has one more H plus. So obviously you add an H to water, you get H3O. And if you add the plus, you get +1 in that particular case. So acid conjugate base pair. Any questions on the relationship there? Yes. Yeah, so in this function is going to act as a base, and it can in certain cases act as an acid. Basically, if you throw in a base into water, basically, yeah. It would, yeah. So that's why it's referred to as being an amphoteric substance. It's a substance that basically, depending on the situation, could act either as an acid or a base. Yeah, we'll see some, but a lot of times the ones that are able to kind of do that are things that have a hydrogen, and a lot of times a negative charge. You know, so for example, something like HSO4 minus, something like that, has the hydrogen, so it could give the hydrogen, so act as an acid. and it also can accept an extra hydrogen here as well. So it has the ability to do both. So a lot of things that could kind of go both ways are things that kind of look like this. The key part of that a lot of times is it has a hydrogen and it's got like some type of negative charge, and that's usually something that can kind of go both ways and behave that way. Clearly, if you had something, for example, like, say NO3 minus, this could not act as an acid ever because obviously it does not have an H to give, right? So that's the definition of an acid. Can in certain cases act like a base, or I'll go NO2 minus, that's probably a better example. That can act as a base and accept the H plus, but it will never be able to act as an acid and give away something it doesn't have, obviously, to do. Other questions? Okay. So here again is that reaction just sort of drawn out, and as a result of this guy being over and being accepted, and once again, H3O plus, pretty much kind of the same thing as H plus, so they're essentially equal to each other. All right, so why don't we try one here for each of the following, decide whether these guys are basically conjugate acid-base pairs. So take a minute or two to see what you come up with. So really the question is the difference we're looking at just basically one H plus? So there's a couple ways you could do it. Obviously, you could just take the two things, look at them, I suppose. No, you can. And when you lose not the H, just the H, but the plus, you become one more negative. And that gets us the same thing on that side. So yes, these two things related to each other, as the only difference is one H plus. When we look at the second one here, we have HCl and ClO minus. These two. So another difference, this guy has an oxygen, this one does not have an oxygen, which means that it makes them not a pair. Again, the only difference can be an H plus difference between them. Any questions on that one there? And HPO4 2 minus, once again, look at if you want to take away an H from the guy on the left, that leaves you one H, which is HPO4. And again, when you lose the H plus, you become one more negative, which is -2. So these guys are a pair in this case. And lastly here, HNO3 and NO3 minus. Once again, if you sort of take away the H and you lost the positive, makes you one more negative. So those two guys are related to each other and they would be a pair. So it looks like everybody's a pair here except number 2, right? Any questions on that there? Obviously, you could do the other. You could just put the H plus on. So you put an H on that, and +1 -1 gives you 0. And obviously, you get back to the other guy. So they match each other. So 1, 3, and 4 here look like all pairs. Any questions on any of those there? So why don't you try this one here? I was in a situation like this, talking about in terms of the equation. So remember on the left-hand side, you have acid and a base. On the right-hand side, you have the conjugate acid and the conjugate base. But on one side, so in this particular, to give the conjugate with and Chem acid is something that will donate the H plus. So that is the key, and where people screw up is they know it should be an H plus, but they're not sure if they should put it on or take it off, and that is what you want to really determine in this case. For all these guys will behave as an acid, which means we should just take off an H and a plus. When we take off the H for the first guy, we are left with one H and an S. positive, you actually have like more negative charge. You become one more negative, and it would be HS minus in this case. That is something people always forget, is the positive part of it. It does affect the overall charge of what you get on the conjugate base or conjugate acid. So you want to make sure you keep an idea on that. Same thing here. This is again going to act as an acid. So we're going to toss out the H. That's going to leave us just an S. We already are -1, so we become one more negative. So we go to -2 in this case, which would be S2 minus. In this case here, we're going to once again lose the 1H. That leaves us a nitrogen and 2 H's. Once again here, we were no charge, so we lost the positive. We become one more negative. And lastly here, we're going to dump an H. We're going to leave us one H, an S, an O, and a 3, and a minus. So again, if you were asked to do the conjugate acid, you could go backwards and accept an H. You would put an H plus on from conjugate acid or conjugate base. Any questions on that there? Why don't we try one like HCO3 minus? Why don't you do the conjugate acid, and why don't you do the conjugate base for this guy? On our same logic, we'll start with the guy on the left there. We're going to go for the conjugate acid here. So once again, if you're not sure, this relationship could help you. If I am looking to end at the conjugate acid, that means what I am starting with is a base. And the definition of the base based on Bronsted Lowry is it's going to accept an H plus, which means we should put an H and a plus on this. And when you do, you end up with H2CO3. One more H there, and a +1 -1 gives you 0 in terms of the charge. You end up with basically carbonic acid. Any questions on that one there? Now, if we were looking for the conjugate, yeah. What's that? You don't, what we are doing in this case is basically because we're looking for the conjugate acid, this guy is going to accept an H plus. So the H gives us to the 2 H's total, but it already had a -1 charge. So -1 and +1 gives you 0. So the guy on the left there should not have any charge at all. Basically balances out. Other question? Now, if we're looking for the conjugate base, once again, you can use this relationship like we did previously and see that we then would be starting with an acid in this case, which means this guy is going to donate the H plus. So we actually want to take the H and the plus off. When we take the H off here, we end up with just CO3. Once again here, it lost a positive, so it becomes one more negative, and it becomes carbonate in this case, CO3 2 minus. This is once again a thing that could act obviously as an acid or a base. This is your amphoteric type substance, and as I mentioned before, very common features. An H and like a negative charge has the ability basically to go both ways. Any questions on acid conjugate base pairs here? So let's talk a little bit about acid strength here. If the forward reaction of an acid and water, at some point it can kind of go back the other way. So at some point the products here can recombine once they sort of reach a certain level and head back the other way. In this situation, this is really what happens with a weak acid. And again, we know it's a weak acid because we do see those arrows heading in both directions, meaning that is a weak electrolyte. So an example of this would be something like hydrofluoric acid, which is a weak acid, plus some water. And once again, because this is an acid, it's going to donate its H plus over. The result of that will result in H3O plus and F minus. Now, basically, these guys are weak electrolytes. And again, if you remember with weak electrolytes, pretty much what you have in solution is the guy on the left-hand side, pretty much still stay together, but it's able to produce a little bit of H3O plus in solution. So since it's able to produce a little bit of H3O plus in solution, it's still considered an acid, but it's a much weaker acid, as I mentioned, than something like hydrochloric acid, which is going to 100% break apart in solution and produce a lot of H plus very, very quickly. Any questions on that there? Now, if the forward reaction predominates, we do have a strong acid situation, and it will 100% completely ionize. A reminder of some strong acids, which I think I put on the board when we were talking about something, I think, in an earlier chapter. But some strong acids are hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. So these are some very common strong acids. Almost for the most part, if it's not one of those, you could probably safely assume that it's going to be a more weak acid. So some weak acids are like acetic acid, hydrofluoric acid, but these are kind of your main list of strong acids. What each of these share in common is when they are in solution, pretty much 100% of it breaks apart into ions, like we talked about with strong electrolytes. So in solution, 100% is the H plus and Cl minus floating around that solution. Absolutely none of these guys still there in solution. And that is really why they are a strong acid, because it produces a lot of free H plus really quickly. And again, the weak acid will kind of stay together. Like HF is a weak acid, as I wrote on the previous slide there. Acetic acid is a weak acid. Nitrous acid is a weak acid. Carbonic acid is a weak acid, and so forth. So these are some weak acids. And like I said, the easier move probably is just to remember these guys. They do come up a lot in future chemistry classes. And if it's not one of those guys, probably a pretty safe bet that it's more a weak acid that you're dealing with. Any questions on that there? All right, we will lay it up there for now.